Well, hi everyone, and greetings from Northern Michigan. This is Bob the Science Guy. You know, the other day, Brian's Logic, one of our flat earth scholars, decided to do a piece, quote-unquote, debunking me on the Haversine Formula. Today, I'd like to go ahead and have a look at that because I found it quite amusing. I'm going to explain what the Haversine Formula actually does, in contrast to what Brian thinks it does, and how it's used to confirm that the Earth is indeed a globe and rule out the possibility that it could be a flat Earth. So let's cue up the music and get going.
Well, how are you doing? This video is called Bob's Haversine, and it's for Bob the Science Guy, because he's doing something at the moment that is making claims at the moment that are really, I don't even want to call them sneaky because they're not, they're terrible, right? This is terrible, right? This is the Gleason's map. I'll come back to this in a while. You'll understand why I'm showing it in a couple of minutes. First of all, I want to show this. Bob the Science Guy is using the Haversine Formula, right? And he's stating that with the use of the Haversine Formula, that the distances that he's been able to measure on a globe match reality, right? On the surface of a globe match reality, whereas the straight line flat Earth distances don't. This is what he's saying. But we all know that the shortest distance between 2 points is a straight line.
Okay, so let's take a moment and unpack what he's talking about here. Now, there are two ways of looking at the Earth when you're looking at flat versus globe. Now, on a flat Earth, we can use the Gleason's map as a good example of a flat Earth. Now, what you see on the Gleason's map there is a triangle that I drew with blue masking tape. And that triangle goes between Sydney, Australia, the North Pole, and Perth, Australia, and then back to Sydney. Now, we can tell the distance involved in two of the legs of that triangle, the distance from Sydney to the North Pole and the distance from Perth to the North Pole. We know the angle at the apex of that triangle near the North Pole is 35.35 degrees, which is the difference in longitude between Sydney and Perth. Now, given that information, we can solve for the third leg of the triangle, specifically the distance between Sydney and Perth.
This is more another thing on the Haversine Formula. Same again, you have a distance here along the surface here of this sphere or circle, and you have two radius lines. Shows it again, right? Radius lines, and you have a distance here along the surface of this circle, right? So the only way you can get the distance along the surface of a circle is to use a radius line.
Now, we're going to go over this a little bit more later, but he's got it wrong from the get-go. What the Haversine equation does is it finds that angle alpha that's directly over my head. That is the angle formed by drawing a ray from the center of the Earth to your starting location, and then drawing a second ray from the center of the Earth to your ending location. Those two rays will form that angle alpha, and that's what the Haversine equation is designed to do. You then apply the Haversine formula to find one of two things, depending on what information you start with. You either find the distance along the surface of the sphere between those 2 points if you know the radius of the Earth, or if you know the distance between those 2 points because you drove it and measured it, you can use that to find the radius. We're going to do both. But let's let Brian continue.
So the only way you can get the distance along the surface of a circle is to use a radius line, right? You need a radius value to know what it is, right? You need a radius value. Now, the Haversine Formula is used, right, for what the globers call, globe believers call great circle distances, right, or great circle routes, right? Mostly it's used with use of them, right? All great circle routes really are, right? What they mainly are is north to south, right? Longitude lines. That's all they are. Majority of it is just north to south distances, or mostly north to south longitudinal distances. I would like to see all these great circle routes done and completed, and people ended up back where they started. That would be really interesting.
Now, before we go much further, let's go ahead and correct Brian's understanding of what a great circle is. Now, he is correct partially, and that is that all lines of longitude, including the minutes and seconds and every subdivision of a second, are actually great circle courses, because what they do is they go all the way around the Earth and then come up again on the other side. However, you can do that from any point on the Earth. Let's say we go from London, England, and look at what's called its antipodal position. Now, London is at approximately 51 degrees north latitude. Its antipodal spot will be directly opposite on the Earth at 51 degrees south latitude. And if you look at, say, the prime meridian, as it goes around, it will come around the other side and intersect the 51 degree south latitude at a position on the Earth that is directly opposite of London, England. And if you have another spot, such as New York City, and you want to rotate New York City, you can continue a line between London and its antipodal spot that goes through New York City. The segment of the line from London to New York is the circle course between those two. Now, for those of you keeping score on Science Denial Bingo, I want you to look at this illustration that Brian uses to make his point that great circle courses only go along lines of longitude from north to south. In his own example, he is showing a great circle going between London, England, and San Francisco, California, which is most definitely not north to south. It's more northeast to southwest. But don't let facts get in the way of your narrative, Brian. Do continue.
I'm going to show what Bob is doing. So, some time ago, Bob was on Nathan's show, and he tried to use a chord as the base of a right triangle. And I pointed out to him that the chord was less than the arc that resides above it. So when you bring a chord through a circle, right, the arc that resides above it is greater in length than distance, right? So the chord is always going to be less in length and distance than the arc. And I pointed out to him that he can't use a chord for a right triangle to get a straight line distance on a globe Earth, because the chord is going to be less in distance. So the coordinates are not going to match, right? Because if you bend the chord, it will only go maybe 3/4 way or 6/8 or 7/8 of the way of this. If let's say the length of this green line will only go to, from this point here, will only go over to about here.
Well, he flubbed that one up pretty badly. So let me go ahead and clarify what he didn't understand on Nathan's show and doesn't understand yet. I went on Nathan's show to do exactly what I'm doing today, and that is show that distances between 2 points on the surface of the Earth effectively rule out the flat Earth. He is referring to a question that he asked me about the shortest distance between 2 points would be a chord, wouldn't it? And the answer, of course, is, well, yes, but the shortest distance between 2 points on the surface of the Earth is a great circle. And then he got fixated on the chord, claiming that somehow I was using the chord in the Haversine Formula. The chord is not used in the Haversine Formula. The chord is used to prove the Haversine Formula. So let's go ahead and clarify this so that he understands it a little better. Now let's go ahead and just have a look at two things. The first one is going to be the Haversine Formula. Now, I'm going to go ahead and just draw a couple of marks on this protractor right here. And then we're going to get rid of the protractor because we no longer need it. So let's say that our starting position is somewhere along this ray that starts at the center of the Earth and goes off into infinity. And our ending point is somewhere along that ray, which also starts at the center of the Earth and goes off into infinity, and our ending point is somewhere along that line. We don't know where. Now, right here, there's an angle, and this is called angle theta. Now, in order to find angle theta, what we can do is use a little bit of trigonometry and something called the Haversine Formula. Now, the way the Haversine Formula works is that we divide this angle in half, right here. And even though we want angle theta, which is this entire angle here, what we can do is we can solve, and that angle, we'll call that alpha. Angle alpha equals angle theta divided by 2. Angle theta equals 2 alpha. So notice that there is absolutely no radius involved in any of this. What we're doing is we're employing the Haversine formula to find the Haversine, which we're calling angle alpha, in order to determine what angle theta between the starting point and the ending point and the center of the Earth. Now, we're going to go over that a little bit more in a few minutes, but before we do that, I'm going to show you how we're going to find the length of a side of a triangle if we know two sides of the triangle and the angle in between them. So, for example, what we're going to do is we're going to take a line to Perth, Australia. And then we're going to take another line from the North Pole to Sydney. Now, Perth is at longitude about 115, and Sydney is at longitude about 151. So this angle right here is going to be 35.35 degrees. Now, let's go ahead and see if we can figure out how far it is between those 2 points. So we're going to go to the Gleason map and work on this first, and then once we have this distance on the Gleason map, we're going to compare it to the Haversine distance, and then we're going to compare it to reality. Now, to start off this hoedown, I went ahead and got my Gleason map, and what I did was I marked a line from the North Pole to Sydney, from the North Pole to Perth, Australia, and then from Sydney to Perth. And I measured those with a ruler. So here are my results. The distance from the North Pole to Sydney is 6.5 inches. The distance from the North Pole to Perth is 6.25 inches. And the distance from Sydney to Perth is 3.85 inches. And as you can see, there is me taking the measurements so you can confirm that those are accurate. Now the fun begins. We use something called the Law of Cosines to find a side on a triangle where we know the length of two sides and the angle in between them. And here is the Law of Cosines. There's a couple of different ways to write it. This is the way I happen to. So the cosine of this angle C equals side A squared plus side B squared minus side C over 2 times side A, side B. Now, to rearrange that to solve for C algebraically, this is what we end up with. It's the square root of A squared plus B squared minus 2AB cosine C. Well, we've got our numbers right here. This is side A, this is side B, and that's side C. Now, we measured this directly, but the Gleason map is a little inaccurate out in the periphery when you go east to west. We're very confident with these measurements, so we're going to use the Law of Cosines to see what side C should work out to be. And let's go ahead and put the numbers in. So here we go, folks. Caution, math ahead. Side C will be the square root of this entire term right here. So we have 6.5 squared from the distance from the North Pole to Sydney. We have 6.25 squared, distance from the North Pole to Perth, times 2 times 6.5 times 6.25, that's the 2AB here, times the cosine of the difference in longitude between the two, which is 35.35 degrees. Now, I've got the answers here, and I've added them together to get 81.31. This term here reduces to 68.95. So the answer is going to be 12.36. We're going to take the square root of that, and we're going to get 3.51. Now, that's a little bit different than the 3.85 we got by direct measurement, but that is the difference between calculating based on longitude and trying to measure based on a 100-year-old map that has limited accuracy in that part of the world. That right there is the most reliable distance. Now, if you try and use a scale for this, you're going to find that on the measured distance and the calculated distance, you're going to get a slightly different number of miles per inch. It's going to be 1143 and 1170. If we add those together and divide it by 2, we get an average of 1,156 nautical miles per inch. Based on this number, the distance between Sydney and Perth is 4,059 nautical miles. And based on this number, the distance between Sydney and Perth is 4,481 nautical miles. So based on what we just did, our distance from the North Pole to Perth is 7,317 nautical miles, right there. The distance from the North Pole to Sydney is 7,432 nautical miles. So therefore, the distance here is going to be somewhere between 4,059 and 4,481 nautical miles, depending on which scale you end up using. Now, the Haversine formula seems like it's a little complex, but it really makes a lot of sense. Say this is the longitude and latitude of your starting position is going to be somewhere along this line, okay? And the longitude and latitude of your ending position will be along this line. Now, the way the Haversine formula works is it compares the arc distance between those 2 points and calls that d. To determine what d is, we need to first find out what this angle alpha is, which is the Haversine, and use that to find angle theta, which is the angle between your start point and your end point. Now, for example, if this line was going due north and due south, you would have a change in latitude, but no change in longitude. If it was going east and west, you would have a change in longitude, but you would have no change in latitude. In most cases, it's somewhere in between. So let's go ahead and look at the Haversine formula. A couple of things to begin with first, though, over here on the left side. First of all, the change in latitude between Sydney and Perth is 1.92 degrees. The change in longitude is 35.35 degrees. The latitude of Sydney is 33.87 and the latitude of Perth is 31.95. Now, these are just some trigonometric identities to refresh ourselves with. If you look at an angle of 0 degrees, the sine would be 0, the cosine would be 1. If you're looking at a 90-degree angle, the sine would be 1 and the cosine would be 0. And the Haversine of angle theta is the sine square of angle theta over 2. So let's see what we have up here. So the Haversine is right here. And that's sine square of angle theta over 2. And that equals the sine squared of the change in latitude divided by 2. Recall that if there's no difference in latitude, this will be 0, the sine square of 0. And the sine of 0 is, of course, 0. So that term would drop out. So once you've taken into account the latitude, you have to take into account the longitude. And the way that you do that is you get the cosine of latitude 1 and latitude 2, and here they are right here. And that is multiplied by the sine square of the change in longitude divided by 2. So let's break this down and put the numbers in for Sydney and Perth. All right, so I've gone ahead and I've put the values in from over here on the left. Sine square of 1.92 over 2 equals 0.000281. Likewise, here's the value for cosine of 33.87 degrees, cosine of 31.95 degrees, and sine squared of 35.35 over 2. We bring these all together, and we come up with a Haversine of 0.00281. 14.0653. We have to take the square root of that, and to do that, we'll hit the square root function. Next, we have to take the arc sine of this number, which is the sine of 1/2 of angle theta. So make sure that it's on second, and then just hit the arc sine function. And that comes up to 14.81. So we'll put that 14.81. And then since that's half of angle theta, we have to multiply it by 2. And that comes up to 29.61 degrees. We can take 29.61 degrees and multiply it by 60 nautical miles per degree. That gives us 1776.6 nautical miles. Okay, so by calculating it by the Haversine equation, the distance between Sydney and Perth should be 1,776.6 nautical miles. It should be pretty easy to tell the difference between the two. I mean, this is more than double that. Well, let's finish this up. The Haversine equation is what we use to find angle theta. The Haversine formula, that's how we find the distance between 2 points. So, what's the formula to find the distance between 2 points? Well, there are 2 ways that we can do it. We just demonstrated one. If we know the number of degrees times 60 nautical miles, equals the distance. The other way that we can do it is using something called radians. If you look at this distance right here, the radius, there's going to be a segment of that circle that is equal in length to that radius. So there would be 2 pi radians in 360 degrees. So right here was our Haversine. We're going to go ahead and take the square root of this number again. Then what we're going to do is we're going to take the arc sine, but this time we're going to hit radians instead. So we've got the arc sine, and there it is. This is the number of radians in 1/2 of theta, which is the square root of the Haversine. We're going to multiply that by 2. Then what we do is we multiply that by the radius of the Earth, which is 3,440 nautical miles. Same thing we got the other way. But there's something that's interesting that we can do with this. So if we take our formula, which is 2 times the radius of the square root of the Haversine, actually the arc sine of the square root of the Haversine, that will equal the distance across the ground. Well, what if we don't know what the radius is? Well, that's no problem at all. If we know the distance across the ground and we divide it by 2 times the arc sine of the square root of the Haversine, that will equal the radius. Now, it should already be apparent from our Sydney to Perth trip that we had the radius of the Earth because we put it in. So just to finish things up, let's go ahead and use Brian's great circle between San Francisco, and here's the latitude and longitude, and London. Again, here's the latitude and longitude. We've got our delta lat and our delta log here. We've done the Haversine formula, and we came up with a Haversine of 0.6765 radians. Now, 2 times the radius times 0.6765 would equal the distance between London and San Francisco. We can rearrange this a little bit to take the distance between London and San Francisco divided by 2 times 0.6765, and that will give us the radius of the Earth. The measured distance between San Francisco and London is 8,605 kilometers. Divide that by 2 times the Haversine. We get a radius of the Earth of 6,359.9 kilometers, which is approximately 10 or 11 kilometers off the accepted value. So Brian, just a little bit of advice. If you're going to try and discuss something called the Haversine, you should know what the Haversine actually does. So not only did you misrepresent what it was and how it worked, when the proper methods were used, not only did we verify the spherical Earth and exclude the flat Earth, We also verified the radius of the Earth using your own example. So better luck next time, sport. This is Bob the Science Guy signing out from Northern Michigan. Thank you again for stopping by. Please take a moment, hit that like and subscribe, and remember, I really appreciate all my Patreons, channel members, and subscribers. I'd like you to be one or three of them.
Mama, please make them hear me, or I can't teach them anymore. This rabbit hole's too deep for me. Feel my brain getting real sore. Bob the Science Guy. Bob the Science Guy.